Why is this weird matrix product defined that way? Is it possible to interpret it? Yes! Today I'm going to show you how to visualize geometrically matrices. This will make algebra much more intuitive for you. In fact, you will be much more comfortable finding eigenvalues and eigenvectors, and matrix calculation will be easier for you. So stay focused, let's go. I considered a 2x2 matrix to show you quickly that the geometric interpretation of matrices boils down to plotting the vectors of the standard basis of the plane or the 3D space if you want to visualize a 3x3 matrix, and what we will call their respective images by the matrix considered. That is, each of the vectors returned when we multiply each of the vectors of the standard basis by the matrix considered. In order to understand the principle on which this geometric interpretation is based, I'd like firstly to define what is called the behavior of a matrix to show you that a matrix is quite similar to a function that takes a vector in a certain vector space and returns another vector in the same vector space. We will call the vector returned by a matrix when this matrix is multiplied by another vector an image vector. I proved the following equivalence in a previous video, where F is the endomorphism canonically associated with the matrix A. If you didn't see this video, that's not a problem, but I recommend that you see it to have a better understanding of how an endomorphism is associated with a matrix. You can find the link in the description. Let's now consider a 3x3 matrix. For a 2x2 matrix, it's the exact same reasoning. You can see through this equality that in order to determine the behavior of a matrix, we just have to derive the product of the matrix and each of the vectors of the canonical basis. To do so, I advise you to keep in mind the following. When the matrix is multiplied by the ith canonical vector, where I is between 1 and the size of the matrix, the result must be equal to the ith column of the matrix. You could simply derive it by using the definition of the matrix product, but it's much more convenient to say it like this, especially when you want to visualize geometrically matrices. For instance, when this 3x3 matrix is multiplied by the vector 1, 0, 0, which is the first canonical vector of the 3D space, the product must be equal to the first column of the matrix. To come back to the interpretation process, when you finish plotting the 6 vectors in this case, or the 4 vectors in 2D, you have to focus on the image vectors of each of the vectors of the standard basis. I plotted them in blue here. If one of these image vectors is collinear to its antecedent vector, then you've found an eigenvector and therefore an eigenvalue. If two of these special image vectors are collinear, then you can find a linear combination of the two corresponding antecedent vectors, such that this linear combination is an eigenvector corresponding to the eigenvalue 0. By deriving the product of the matrix and each of the vectors of the canonical basis, it's then almost instant to derive the product of the matrix and another vector taken in the space in which we work, that is the plane or the 3D space. For example, A times the vector 1, 1, 1 is equal to 1 times A times the first canonical vector plus 1 times A times the second plus 1 times A times the third. So A times 1, 1, 1 is equal to the sum of the vectors plotted in blue here. So we almost instantly figured out that A times 1, 1, 1 is equal to the vector 0, 0, 2. Try now as an exercise to interpret geometrically this matrix and understand why it's called a rotation matrix. I'll do it in the next video. Well, hope you enjoyed this video. It took me days and days to create it, so make sure to leave a like and subscribe. And thank you very much for watching, guys. Bye bye.